Alright, so the example we're going to look at is f of x equals negative 2 times the quantity x minus 3 squared plus 8. And I think it's very important for us to identify right away what the a, h, and k values are. So if you look at this equation and you compare it to the vertex formula, f of x equals a times x minus h squared plus k, then you'll see that the a value is negative 2. The h is going to be 3. Now notice I changed the sign because the minus doesn't come along with the h. Okay, so you take the positive value, change the sign as you bring it out, and then the k value is whatever's on the outside there, that's your 8. Alright, and so I can get a bunch of information about the graph of this thing. First of all, the vertex. The vertex is simply h comma k, so it would be 3 comma 8. The axis of symmetry is an important one. Axis of symmetry is going to be the equation x equals, it's going to be the h value, which is 3. That's your vertical line. I also know one other interesting feature is that this is a graph that opens down because the a value is negative. So this is going to open down and be stretched out. Okay, because the 2 is bigger than 1 essentially. So it's opening down and stretched. In addition, if I wanted to find the intercepts, just so I can get some things to plot here, the y-intercept, probably the easier one to find, is just f of 0. So you get negative 2 times 0 minus 3 squared plus 8. If I simplify this, let's see, f of 0 will be negative 2 times negative 3 squared plus 8. Negative 3 squared is 9, so negative 2 times 9 plus 8, which is, let's see, negative 18 plus 8, which is negative 10. So the y-intercept then would be 0 comma negative 10. That's a good point for that. X-intercepts. I can, first of all, I can tell you that they're going to be x-intercepts because the vertex is above the x-axis and the y-intercept is below. And so somewhere in between, the graph will cross the x-axis there. So x-intercepts. Again, you're going to put the 0 in for the function value. So we get 0 equals negative 2, x minus 3 squared plus 8. To solve this, I'm going to go through and use the square root property. I got to isolate the quantity squared. So I'm going to subtract an 8 from both sides. I get negative 8 equals negative 2 times the quantity squared. Get rid of the negative 2, it's multiplied, so I got to divide it out on both sides. That gives me 4 equals x minus 3 squared. Whoop, there we go. Then I have to use the square root property. So when we use the square root property, it eliminates the square on the right. On the left here, I need plus or minus the square root of 4, which is 2. Okay, it's like taking the square root of both sides. I've seen that in the past, right? So you take the square root, but you have to add in the plus or minus on the other side. Okay. Then I want to add my 3 to both sides. That way I isolate the x. And then I'll kind of swap these around so that x is actually equal to 3 plus or minus 2. And if I just take those two numbers, one with the plus one with a minus. 3 plus 2 is 5. 3 minus 2 is 1. Right? And so that tells me there are two x-intercepts. One of them is at 5, 0. The other is at 1, 0. Good. Now, there's one other very important point that I want to mention, and that is every point has a point of symmetry across the line of, or the axis of symmetry. And so the x-intercepts are both symmetrical, and that's kind of interesting because the vertex is at 3, so these should be equal distances on either side of 3, and that makes sense. This is 2 away on the right, this is 2 away on the left, and so they're the same distance away. But I should also have a point of symmetry with respect to the y-intercept. So I'm going to call that the point symmetric, I'm abbreviating here, to the y-intercept. Now on this one, what's going to happen is the y value is going to be the same, the symmetric point, so it's going to be at -10 high. It's the x value that's interesting here. If it's symmetrical to the vertex, then its distance must be the same as the distance to the y-intercept. Well, the distance between the vertex and the y-intercept is 3. And so then I need to go 3 more to the other side of the vertex, which would make that 6. Okay? So that's going to be 6 and -10. Now what I'm going to do is try to plot all of this information on a graph. It's like magic. The axes just appeared. Let's plot all this stuff in here. The vertex was at 3, 8, so 1, 2, 3, and then up. Well, actually, I can just sketch the axis of symmetry first. That's at x equals 3. So let's sketch that in. That's the axis of symmetry. Use a dashed line because it's not really a part of the graph. It's just a feature that we're going to use to help sketch this out. The vertex was at 3, 8, so 1, 2, 3, 4, 5, 6, 7, 8. So right there's our vertex. I know this opens down, so I'm going to go ahead and label that 3, 8. And this line is x equals 3. Alright, I need my y-intercept, which was at -10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the point symmetric to the y-intercept, this is that interesting point, was at 6, -10. Notice that you have to go 3 over to get to the axis of symmetry, and then 3 more over to get to the symmetric point. So those 2 points are going to be at 0, -10, and then at 6, -10. Okay. The 2 intercepts, the x-intercepts, are at 1, 0, and at 5, 0. Alright, so that one is at 1, 0, and 5, 0. There they are. Okay, that gives us a pretty good idea of what this graph will look like. From there, all we have to do is sketch it in. Alright, it's very steep. We did say it was going to be stretched, and it is opening down. Not too bad on that side. This is harder than it looks. And it probably looks hard. Okay, not too bad. And there's our graph. So this one has 2 x-intercepts. Some interesting things about the vertex form, actually any parabola, is that many of them will have 2 x-intercepts, but it is possible that your graph may have 1 x-intercept, which we've seen before, ones that where the vertex is right on the x-axis. And we've also seen some, well, we haven't seen them yet, but we may see some where the graph does not have any x-intercepts. In a case like this, it might be that the graph is shifted so far down that it never gets up high enough to hit the x-axis. Or if it's opening up, it may be shifted so high that it never comes down and hits the x-axis. Okay, so that's possible. So you could really have 0, 1, or 2 x-intercepts, all depending upon the function being worked with. Finally, last thing I wanted to mention with this vertex form is that you could expand the vertex form. So let's take a look at this real quick. Negative 2 x minus 3 squared plus 8. This is the equation I just plotted. If I were to expand this out, I could put it in the standard form. We'll talk more about the standard form shortly. So remember that a quantity squared is multiplied by itself. It's negative 2 times x minus 3 times x minus 3 plus 8. If I go through and distribute the x minus 3's, I'm going to do this in one step. You'll end up with x squared minus 6x plus 9. Then you distribute the negative 2 in. Alright, so we get negative 2x squared plus 12x minus 18. That 8 is still hanging out. And then I do that final combination. I get negative 2x squared plus 12x minus 10. Okay? And now we have a standard form. In fact, this looks like what we did when we solved quadratic formulas, or solved using quadratic formula in the last section. But now what's interesting is that the a value in the ax squared plus bx plus c, I'll write that out, plus bx plus c. So it looks like the quadratic formula, what we used for a quadratic formula. The a value is the same as the original a value in the vertex form. And also notice the c value ends up being the y-intercept. It's kind of interesting when you expand that out. Okay,